Hi there! In the previous video you encountered some quantities that describe the dataset. Hence the name descriptive statistics. You've seen the minimum and maximum, the mean or average, and the median. Let us focus on this median for a bit. In an ordered dataset, the median is the central value. Recall the dataset containing 20 aspect ratios of the Shoshone-Parfletius, which you see here. Here the median was 64.1, the average of the 10th and 11th observations. Well, this idea can be generalized to define so-called quantiles. The median is a 50% quantile, since 50% of the observations is to the left, and hence also 50% to the right. But we may also look at a 25% quantile. This one also has a name. It is called the lower quartile, quartile with an R for 1/4, 25%. It's usually denoted Q1. Loosely stated, this is the value for which 25% of the dataset is less than or equal to this number. In our dataset, it is the 5th observations, 60.6, since 25% of 20 is 5. Similarly, the upper quartile is the 75% quantile. 75% of 20 is 15, so in our dataset this is the 15th observation, 67.2. This leads to a not very precise definition of a quantile. The p% quantile is a number such that p% of the observations is less than or equal to this number. Now, you may wonder whether this is the right way to do this, because you may spot some strange things. For one, you may be surprised that the lower quartile is the 5th observation, starting from the lowest one, whereas the upper quartile is the 6th observation, starting from the highest one. You may have expected these two to be symmetrical. Moreover, with this definition, the median would be the 10th observation, since 50% of 20 is 10. However, we just defined the median as the average of the 10th and 11th observation. Well, all this is actually just a matter of convention. It is often done in different ways as well, as you can see here. The main idea is always the same though. For the 75% quantile, you want 75% of the observations to be less than or equal to this value. Most of these techniques also need some kind of interpolation, since taking a percentage of a number of observations does not always give an integer. Let's not dwell any further on that though. The important thing is that you have an idea of what these quantiles represent. Especially the quartiles Q1 and Q3 and the median are often used. In particular, they are used for the construction of a box plot. A box plot is a graphical representation of the dataset where a box is being drawn from the 1st to the 3rd quartile, with a line at the median. This is quite sensibly called the box. It can be constructed vertically or, as we are doing here, horizontally. The length of the box, which clearly is the difference between the 1st and the 3rd quartile, is called the interquartile range, IQR for short. In our example, it is 67.2 minus 60.6, which is 6.6. Then whiskers are added, both upward and downward. The upward one extends to the largest observation, that is within the 3rd quartile, plus 1.5 times this IQR. In our case, Q3 plus 1.5 times IQR is 76.2. The highest value in the dataset, which is at most 76.2, is 74.9, so that is where the whisker ends. All values that are even higher are indicated separately. The downward whisker is being constructed similarly, along with the even lower values, which we don't have in this dataset. Such a box plot gives a first idea of the dataset. You may spot asymmetry, for instance. It is, however, particularly useful to compare two or more groups. Let's see how you can obtain this in R. For instance, here we have a data file containing the body length of 111 adolescents, along with the code for their gender, 1 for male, 2 for female, and the body length of their father and mother. We can use the command boxplot father-mother to create boxplots with these two variables. Of course, we are not restricted to 2 groups. And similarly, if we want to compare the body length of the 2 gender groups, we can do so with the command boxplot adolescent tilde gender. In this case, R will consider the second variable, in our case gender, as a categorical variable. For each value of this variable, a separate boxplot will be constructed. We used the IQR in these boxplots. This interquartile range is clearly a different type of measure from the mean and the median. The mean and the median, they give information about the center of the dataset, each in their own way. The IQR, however, tells you something about the spread. How far do observations deviate from each other? Well, there is still another quantity that also gives you information about the spread. It is the standard deviation. Here you see the definition. First we define the variance, s squared, and then the square root of this is the standard deviation. Okay, the definition may look a bit frightening, but if we break it down, it does make sense. Let's compute it for the dataset with the aspect ratios of the Shoshone parflèches. We look at how much each value xi differs from the average x20 bar. That is the second column in this table. If we add the values in this column immediately, we get 0, so that is not very useful. Rather, we square all of them. This gives the third column. And then we take a sort of mean of those squares by dividing the sum of the squares by n-1. And here we get that the s-square value is equal to 85.58. Now, why n-1 rather than n? Well, there are some good reasons for that. We'll come back to it when we talk about estimators. This value s-square is called the variance of the dataset. Since it is an average of squares of observations, it will also have squared units. If the observations are length in meters, for instance, then the variance will be in squared meters. So, take the square root of this variance to obtain the standard deviation, which now has the same unit as the observations. The standard deviation in this example, 9.25, gives you an idea of what kind of differences with the average are to be expected. These quantities can of course immediately be obtained using R. The commands are VAR and SD for variance and standard deviation respectively. Okay, see you next time.